stabilized logical qubits and qudit generalizations of Kitaev model.
Hi, everyone. I'm Aayush from Arizona State. And first of all, thanks to the organizers for the nice workshop and selecting my poster abstract for the short talk. And I'm going to be talking about my work with monitored Kitaev models. And this work I've done with Ezra, who's a postdoc at ASU, and Onur, who's my advisor at ASU. And this work has been recently submitted to arXiv right here. So, uh, as in some of the talks, especially Drew's, it was seen that measurements can be used as ways to tune the entanglement in your quantum circuit. And if you just think about this generic brickwork random unitary circuit with some interspersed local single site measurement operators, then we understand that these unitaries would increase the amount of entanglement and measurements would generally decrease the amount of entanglement. And it's also known well that there is a measurement-induced phase transition depending on the rate of these single-site measurements. But on the other side, people have also shown that just measurements that are anti-commuting and like competing can also tune the amount of entanglement in your circuit, and you can get highly entangled volume laws or area laws just by tuning what kind and what rate of the measurements there are in your circuit. So along those lines, you can think of the Kitaev model, and I don't really need to talk about the Kitaev model too much because Sophie already did. And so there are these bond-dependent interactions and these plaquette operators that commute with the Hamiltonian. That's why it's exactly solvable. And you get this nice phase diagram with a gapless and gap phase. And if you think about the Kitaev model in terms of a quantum circuit, with just qubits on the vertices of a honeycomb lattice. And then if you projectively measure these bond-dependent X, X, Y, Y, or Z, Z bonds, not weak measurements, stochastically, if you stochastically do these measurements with some probabilities Px, Py, Pz, and then in the steady state, you calculate the entanglement entropy, then you get a similar looking phase diagram where in the anisotropic regions, you get a topological area law with this topological entanglement entropy. And in the isotropic region, you get a logarithmic violation of this area law, which I'll call a critical law. And this is well known. So the Kitaev model is nice because it has led to a lot of theoretical understanding of the spin liquids in the last 20, 25 years. And but the thing is that the Kitaev model is particularly fragile to perturbations that don't commute with the flux operators, because then you don't have those infinite conserved quantities anymore, and the topological order is lost. So one way to get around that slightly is by using these gamma matrix generalizations of the Kitaev model, which have an expanded local Hilbert space. And this allows for additional plaquette conserving perturbations that you can add to your model. And also you can go beyond the 3 coordination number that is fixed by the 3 Pauli matrices in the regular Kitaev model. So, and throughout my PhD, I've worked on a bunch of these models and seen interesting physics coexisting with the topological order, like fractionalized Colson modes and altermagnetism coexisting with topological order and some more things. So that's what we'll do. We thought that why not try to see what happens in the quantum circuit picture of these gamma matrix models. And earlier in the previous slide, I showed a gamma matrix version, but you can also write these models in terms of a spin and orbital degree of freedom, because the local degrees of freedom are 4-dimensional. So you can write down a spin orbital model. And and we do this for the honeycomb lattice and the square lattice both. And for both of these models, you have their own flux operators that commute with the Hamiltonian. And because the local Hilbert space is 4-dimensional, you have 6 minor fermions per site if you try to solve this model in the same way that as Kitaev does. And the difference here is that just like in the Kitaev model, you have one itinerant minor fermion, which is coupled to Z2 gauge fluxes. For the honeycomb lattice model, we have 3 flavors of minor fermions, and for the square lattice, we have 2 flavors of these minor fermions that are coupled to the Z2 fluxes. And then I'm just writing down these perturbations, the placket conserving perturbations that I was talking about. For the honeycomb lattice, you can check that a magnetic field term or a Heisenberg interaction term commutes with the fluxes. And similarly, for the square lattice model, you have a magnetic field in the z direction or an Ising interaction term that commutes with the fluxes. This is for later. And so what we do is that we reframe this Hamiltonian picture and take these bond-dependent terms of the spin orbital model, and then again projectively measure them with probabilities p alpha depending on what alpha bond that you're measuring. And then we use because these are Clifford circuits, you can do large-scale stabilizer simulations for the numerics. And we start with a maximally mixed state or product state, doesn't matter. And then you can do these 2 qudit bond operations, like bond measurements for some time, which is not more than polynomial in the system size. And then we see that the plaquette operators are quickly measured and they get added to the stabilizer generators. But because all the bond operators commute to the plaquettes, these don't show any dynamics after that. And then what we can do is we can calculate different entanglement measures to map out the phase diagram depending on as a function of these probabilities. So before moving forward to the entanglement phase diagrams, let me talk about exact mapping that is there between these monitored free minor models to some classical loop model. It's a stat-mech model in a higher dimension. And for our case, instead of a single flavor minor loop model that you see in the Kitaev model, because we have multiple flavors of minor fermions, you have these operators that can fuse together different flavors of these minor loops. And I won't go in much detail because there's not a lot of time, but the basic idea is that if you do numerics, you can find 2 kinds of phases here in this loop models. One with long strings, which shows critical law entanglement, and one is short strings, which shows area law entanglement. But within our model, we see this area law and a critical law with this nice data collapse. But we also see a volume law, and I'll talk about this later. So these 3 phases can be thought of in the following way. One can do purification dynamics, which just means that you start with the maximally mixed state and do these measurements as a function of time and calculate the entropy, not the entanglement entropy, just the entropy. And for the critical phase, the entropy quickly goes to 0 as the state purifies very quickly. Also, if you see in all these phases, initially all of them behave the same way. This is the time window where all the plaquettes are being measured. For the area law, what we see is that the entropy goes to a stagnated value. For here, it's this value is 2, and this just corresponds to the 2 non-contractible loops on a torus that are not measured for exponentially long time in system size. And for the volume law, it's generally seen that for volume law entanglement, purification dynamics exponentially slows down with time. All right, so these measures are great, but we found that measuring the tripartite mutual information is a much better way to label the phases. As for the critical law phase, one can show that there is one string that is shared between the regions A, B, C of this torus, and that's why the mutual information is -1. And for the area law phase, you can show that there are effective Bell pairs that are shared between A and C regions, but not on B or D, and that's why you get a +2 mutual information in this case. So this is what we use to label all of our phases. And now I'll talk about the phase diagrams. So these we can do single site measurements, as I was showing that these magnetic field terms do commute with the Hamiltonian and the fluxes. So we can do these measurements, and these measurements are still bilinear in Majorana fermions. So we can still use the loop model picture to understand these phases. And what we see is that for the honeycomb lattice model, these single site operators that commute with the plaquettes move the phase boundaries in the following way, that there's this non-monotonic behavior where the phase boundary, the phase which contains the critical, the sphere that contains the critical phase, its radius increases first and then decreases. And for the square lattice model, we see this effect much more strongly. Here we have tetrahedrals instead of triangles because the square lattice has 4 kinds of bonds. And we see that as you increase the rate of measurement of these single site operators, the critical law phase just completely disappears. And this area lot that is being stabilized by these pH measurements is the phase where these logical qubits live. So that's why we say that single site measurements, which are like errors, can stabilize these logical this phase, this area law phase, which hosts the logical qubits. And yeah, okay. So just to understand how this non-monotonic behavior arises, we can look at the loop model picture. And if you think about this single site operator Z, you can write this in terms of Cx and Cy Majorana's. And what it does is if you have some X and Y flavor of strings in your stabilizer generators, then this would just fuse together those strings and give rise to longer strings. And because longer strings correspond to the critical phase, that's why a small number of these Z measurements will favor the critical law phase. However, if you mostly just measure the single site terms, then there are not enough strings to fuse together, and you just are left with length 0 strings in your stabilizer generators, and that's why the critical law phase just goes away. And we also do these 2-site measurements, the Heisenberg term and the Ising interaction term. And now the thing is that these operators cannot be written in terms of bilinears, they are interacting terms. And so that's why this critical phase completely turns into a volume law phase. For the honeycomb lattice, we see that this as we increase the strength of these interaction measurements of this interaction terms, these critical, this volume law just takes over completely. And at a critical PJ, this just becomes fully volume law. But we see a different behavior for the square lattice case, where increasing PJ leads to a different distinct area law. And we see that this area law too has 3 logical qubits, and instead of the 2 non-contractible loops that I talked about before. And I can talk about it later, but we show that this area law can be thought of as a coexistence of 2 topological 2 codes. One of them is a regular topological code that comes out of the Kitaev model, and one is a n-qubit repetition code. And that's why we get 3 logical qubits in this phase. All right, I don't think I have much time to go over the take-home messages, but I'll just leave them.
Sounds good.
Thanks.
Any questions? Great.
Yeah.
So I'm not sure if this is possible with the system sizes, but can you say something about the nature of the transition between the volume and area law with the interacting measurements?
So at least, so for the volume law, we're not sure because the loop model picture doesn't hold up here, so we can't say. We haven't done any proper critical exponent studies to see what kind of transition this is, but the other transitions can be understood in terms of the loop models.
I see. And well, maybe one other quick question. So I thought that the loop model was required some special property so that like if I just have a generic bilinear, generic free fermion, Majorana circuit, and I'm monitoring some bilinear, I thought that's not generically equivalent to a loop model. So what is special here?
So I think from whatever I understand, if you, so like here, you don't have just 2 Majoranas, you have 6 minor fermions, but you cannot completely describe this in terms of loop models throughout the purification. Initially, when the plaquettes are being measured, you cannot use the loop model descriptions, but once the plaquettes are measured, then it's just free Majoranas, and then you just have like parity, nearest neighbor parity checks, and that's what I don't really know what are the conditions where the loop models don't work.
I
Like,
see.
yeah.
Yeah, the claim was that there are different signal models for the different free fermion descriptions.
Oh,
but,
yeah.
okay.
Yeah, maybe this is best for over lunch if it's not a short answer, but I was just, this critical entanglement, I was actually more than critical. It's more like a Fermi surface entanglement.
Yeah.
Do you have like a picture for what this phase is?
So, like, as we know that the original Kitaev model doesn't really show this critical entanglement throughout the phase diagram, the original Kitaev model, I mean the Hamiltonian version of the Kitaev model, it just has area law throughout the phase diagram. But if there is some disorder which leads to a Majorana, which leads to a Fermi surface, then that Hamiltonian picture Kitaev model also shows critical law entanglement. So that's what we think that this phase corresponds to, because doing this monitored dynamics doesn't really give us the ground state of the Kitaev model, right? It's something different, and by just comparing the entanglement phases, one would think that this is similar to the Kitaev model with disorder. Yeah, but we can talk about this more. Yeah.
Great. If there's no last questions, let's thank Aayush again for
Thank you.
great work.